In this video, we are going to look at continuous functions. First, we'll define what it is to be a continuous function, and then we'll look at how continuity is related to sequences, neighborhoods, and accumulation points. We'll look at a theorem for discontinuous conditions. We'll look at the sum product quotient of continuous functions, and finally, we'll look at continuity of composition of functions. Bridging what we did in our last video, which was limit of a function. So we looked at a limit of a function at a point C, and it was really independent of the nature of the function at C. In other words, f of C didn't even have to be defined to have a limit of f of C. In this video, though, we are going to look at continuous functions, and that happens when the limit of f at C is equal to f of C. So first we'll look at the definition of a continuous function. So if f goes from some domain to the real numbers, it's a mapping, and we let C be in the domain. We say that f is continuous at C if for every epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of c is less than epsilon whenever x minus c is less than delta. So looking at this pictorially, remember we're thinking of closing in on C. So we're thinking epsilon and delta are very small. So when the distance between x and c on the x-axis here is very small, then we can get arbitrarily close, or the distance between f of c and f of x can be arbitrarily small. That's the idea anyway. This epsilon-delta definition should look really familiar to you, and I probably didn't even really have to give you this graph for you to understand what it means. And the reason why this should be so familiar is because this definition exactly echoes the definition of a limit. So you have a function from D to R, and then if for every epsilon greater than 0, there exists a delta greater than 0, same thing as the limit, then here you have f of x minus f of c is less than epsilon. For the limit, you have f of x minus L is less than epsilon whenever x minus c is less than d. And here is the difference here, this f of c versus the L. And we will see in just a moment in a theorem that when f is continuous and c is an accumulation point of d, then the limit, this L, is exactly equal to this f of c. And there you have why this definition of continuous functions very closely echoes the definition of a limit. A couple of other notations and definitions. So if f is continuous at each point in a subset S of the domain, then f is said to be continuous on S. And if f is continuous on the entire domain, then f is said to be a continuous function. Note the definition requires C to be in the domain, but it does not require C to be an accumulation point. And then we come to the theorem here. In this theorem, we have f as a function from your domain to R, and then f is continuous. First, we see how it's related to sequences. So if xn is a sequence in D such that xn converges to C, then the limit of f of x of n should be equal to f of c. The next equivalent concerns neighborhoods. So this is how continuity relates to neighborhoods. So for every neighborhood v of f of c, so here I have drawn f of c, and in blue, this v is a little neighborhood around f of c. And I can make it arbitrarily small. So my epsilon can be very small because it says for every neighborhood. So even when the neighborhood has a very small epsilon, I can always find a neighborhood u of C, and here I have a neighborhood u of C such that the image of u intersected with the domain is a subset entirely contained in V. In other words, no matter how small this little neighborhood is, I can always find another neighborhood here in the domain that will map entirely into my neighborhood V. And last is how if f is continuous and c is an accumulation point of D, then all of the above are equivalent to f has a limit at c and the limit is equal to f of c. So this is what we were talking about earlier, why the continuous function, why the limit definitions are the same, because when it's continuous, then the limit of f of x as x approaches c is equal to f of c. I am going to leave this theorem without proof. Our first example, let P be a polynomial. Show P is continuous on R. We noted in the previous video or the previous section that for any polynomial P and any real number C, we have the limit as x approaches C of a polynomial in x is equal to, and we could just plug in the C, P of C. This part here, the limit as x approaches C of P of x is equal to P of C, is exactly this statement here. So this is equivalent to f is continuous at C. So in our example, we could say P is continuous in R. We can continue this example to look at this particular polynomial. P of x is equal to 3x squared minus 2x plus 5. So we said that that is continuous at C. And then using this theorem we had from the previous video, which talked about the sum product and quotient of limits. And here's the result, that if we have the limit of f of x as x approaches C equals L, and the limit of g of x as x approaches C is equal to m, and k a real number, then we have the limit of f plus g of x as x approaches C is equal to L plus m. The multiplication, you just multiply the two limits, and if you have a scalar times f, then you can just pull out the scalar. And then also for the division, you could have L divided by m. Using all of these properties, you have the limit as x approaches C of 3x squared minus 2x plus 5 is equal to, pulling out the 3, limit of xn squared, again taking out the squared, pulling out the 2, limit of xn plus 5, which is just equal to, plugging in C, 3 times c squared minus 2c plus 5 is equal to P of C. Our next example, we have the function f of x is equal to x sine of 1 over x for x not equal to 0 and f of 0 equal to 0. So from the graph below, it appears that f is continuous, and we will prove that it is. Using a proof strategy very similar to what we used for limits, we're going to look at f of x minus c is less than epsilon. So plugging in for f, well, here we just started by plugging in c, and at this case, we're looking at f at the point 0. So f of x minus f of 0 is equal to x sine of 1 over x minus 0 is less than epsilon, and we want that to be true whenever x minus c, f of c, or 0, is less than delta. So in other words, we want x sine of 1 over x is less than epsilon whenever absolute value of x is less than delta. And if you recall, we would solve for our x in terms of epsilon. However, this is a little bit difficult, but we can note, because sine goes between 0 and 1, that x sine of x is always less than the absolute value of x. And here, instead of comparing epsilon now to x sine of 1 over x, we're just going to compare that to x, again, because the absolute value of x is always larger. And we're going to keep absolute value of x smaller than epsilon. So x is less than epsilon, and we can take this to be equal, or something in terms of epsilon, to be our delta. And writing everything backwards, when we plug into a proof template, we would say when delta is greater than absolute value of x, that also implies that delta is greater than absolute value of x sine of 1 over x, which is equal to x sine of 1 over x minus 0, which is equal to f of x minus f of 0. That implies epsilon is greater than f of x minus f of 0 when x minus 0 is less than delta, which is exactly what we want to show, or what the conditions we need to show for a continuous function. So these are the calculations you would plug into your proof template, which I haven't provided you, but you can pattern one after the one we had for the definition, a proof template for limits. And now we have a theorem for discontinuous functions, and this relies on the sequence, the relation between sequences. So let f go from D to R, and C is in the domain. Then f is discontinuous at C if and only if there exists a sequence xn and D such that xn converges to C, but the sequence f of xn does not converge to f of C. These two theorems, along with the definition of continuity, are the things you're going to use to prove continuity of a function. So just looking at this theorem here, actually part B, you're not going to necessarily use so much because this involves showing something is true for any sequence, so or all sequences, in other words. So that's a hard thing to show. However, the negation is exactly what this discontinuous conditions theorem is about. So the negation of this is what you use to show that something is discontinuous. This theorem then, to show something is continuous, you can use this neighborhood definition, and we will have an example of that. Or you can use this here, if C is an accumulation point, then the limit of f of x is equal to f of c. Our next example, let D equal the interval negative infinity to 0, union 0 to infinity. So in other words, it's all the real numbers with the exception of 0. And let f of x is equal to 1 over x. I guess that's why we don't want to include 0. Show f of x is discontinuous on R at x equals 0. We want to start by noting, with the exception of x equals 0, the limit of x over c of 1 over x is equal to 1 over c. So f is continuous on D. Again, D does not include 0. F is not continuous at x equals 0. And the strategy we're going to use to show something is not continuous is exactly this theorem here. First, f is not even defined at x equals 0, so it cannot possibly be continuous. But you might recall in calculus, sometimes if there was a function and it wasn't defined at a point, we would define the function at that point in such a way that our function was continuous. In other words, we would set f of 0 equal to some real number, and somehow we could, if we pick the right real number, f would be continuous. But in this case, we can't, that's just not possible. There's no number we can define. F is still not continuous. And the reason is part B of this theorem here. If f is continuous and we have a sequence that converges to our C, then the limit of f of that sequence as x approaches infinity has to equal to f of c. So using this theorem here, first we need a sequence that converges to C. In this case, C is equal to 0, x equals 0. So the limit of this sequence, 1 over n, as n gets large, it does converge to 0. And now we need to compare that to the limit of f of x of n as n goes to infinity. So the limit of f of 1 over n, and in this case, f of 1 over n is just equal to n, so the limit is going to equal to positive infinity, which makes this divergent. In other words, f of 1 over n isn't even convergent. Thus, there's no way to define f of 0 to make it continuous. Here's an example of a function that is discontinuous at every real number. We're going to define the Dirichlet function, which is defined by f of x is equal to 1 if x is rational, and 0 if x is irrational. To show the Dirichlet function is discontinuous, we're going to use this part, the part about neighborhoods here, part C in this theorem, which says that for every neighborhood f of c, there has to be a neighborhood u of c such that f of u intersect d is a subset of v. So let's just consider a random variable, we'll call it c. Then every neighborhood of c contains rational points. And remember, that comes from the density of rational numbers, which we talked about with the completeness axiom. And the density of rational numbers said that between any two real numbers, there's always a rational number. So anyway, our neighborhood, which is an interval around C, will contain rational points, at which in that neighborhood, you're going to have points where f of x is equal to 1. We also had, as an example, that the irrational numbers are also dense in R, which means that every neighborhood of C will contain irrational points, at which the f of those irrational points is going to be equal to 0. So you have f of 1, f bouncing from 1 to 0 in this neighborhood. So in other words, if I take f of x is equal to 1, and I find this neighborhood here, and I want to have a small neighborhood around 1, and then I want to be able to come back over here, and in my domain, I want to be able to find a small neighborhood around whichever rational number evaluated to 1, I'm not going to be able to do that because whatever neighborhood I find here is going to contain something that has f of 0. So I can't find something, no matter how small I get and how small I get here, because these rational numbers and irrational numbers, they're dense in R. So no matter how small I get, I can't find a small neighborhood around C that only maps to 1 or only maps to 0. Thus the limit as x approaches C cannot exist. Hence, f is discontinuous at each point C in the real numbers. We can modify the Dirichlet function so that f of x is equal to 1 over n if x is equal to m over n and it's rational and in lowest terms. So for example, f of 1/3 and f of 2/3 is equal to 1/3. F of 3/5 would equal to 1/5. It would equal to 0 if x is irrational. So f of square root of 2 over 5 would equal to 0. And the claim is f is continuous at each irrational number in the interval 0 to 1, and it's discontinuous at each rational number. We are going to start with the easier proof to show that something is discontinuous, again using this theorem here, at each rational number. So suppose C is a rational number in our interval 0 to 1, and suppose Xn is a sequence of irrational numbers in 0, 1 that converges to C. And this statement here comes from the fact that every real number is a limit of sequence of irrational numbers, and also every real number is a limit of a sequence of rational numbers. And I keep this statement here close to this theorem so I can use it as needed. Since f of xn is equal 0, because our xn is a sequence of irrational numbers and f of x is equal to 0 for irrational numbers, then the limit of f of xn is equal to 0. But f of c, because c is rational, is equal to 1 over n, which is greater than 0, again because c is rational. Thus, the limit of f of xn does not equal to f of c. So we've shown the condition here for discontinuity applies. So f is discontinuous at C. The second part is a little bit longer, so I had to move everything up. So we're going to claim or show that f is continuous at each irrational number in 0, 1. We will start with d is an irrational number in 0, 1, and then also, since it's irrational, by this modified Dirichlet, f of d is equal to 0. So there are two facts we're going to use. So given any epsilon greater than 0 by the Archimedean property, we can always find a natural number k such that 1 over k is less than e. The second note, because these are rational numbers now, or we're going to consider rational numbers, there are only a finite number of rationals in the interval 0, 1 with denominator less than k once you have your fraction in lowest terms. An example of this last note, so if we're looking at rational numbers, in other words, numbers of the form x equals m over n, and we want the denominator less than k, so for example, let's say k is equal to 4. So then our denominator can be 1, 2, or 3. And remember, x is in the interval 0 to 1. Then our only rational numbers where with denominator 1, 2, and 3 are 1/2, 1/3, and 2/3. And remember, because we have to stay less than 1. And just to get a feel for what this is saying, it's related to this note. But let's say d, our irrational number, is square root of 5, which is approximately equal to 2.236. And let's say k, the denominator, we want all the denominators to be greater than k, and let's set k equal to 3. And since we want to set our interval so that all the denominators are greater than or equal to k, so greater than or equal to 3, let's look at the distances here then. How close we can get when k is equal to 2. So the difference between these rationals and d, the closest we can get is somewhere in here between 3/2 and 2, and it's actually at 2, we're only 0.236 units away from d. Now if we set delta to something less than 0.236, maybe delta equals 0.2, then we're looking at the interval the interval 2.036 and 2.436. And in here, the set of rationals in this interval all have denominator greater than or equal to 3. At this point, we've managed to find a delta, so x minus c is less than delta, and then we can also then satisfy this condition of f of x minus f of c is less than epsilon, and we've solved for a k. So I have that written out here. So we're in the interval 0, 1, and we have x minus d is less than delta, then f of x minus f of d is equal to f of x because f of d is equal to 0, which is less than 1 over k, which is less than epsilon, which implies that f is continuous at d. Two other modified Dirichlet functions. The first one of f of x is equal to x if x is rational, and 0 if it's irrational. So the only times that this is continuous is when x equals 0, when these two kind of meet. And so this function is continuous at a single value. Similarly, if I have f of x is equal to sine of pi x if x is rational and 0 if it's irrational, this will be continuous only when these two functions meet. That is when sine of pi x is equal to 0. That is when x is an integer. So this is a function that is continuous only at the integers. Next, we have a theorem relating the sum, product, and quotient of continuous functions. So if f and g are functions and they are continuous, and c is also in the domain, so then f plus g and f times g are continuous at c, and f divided by g is continuous at c if g of c is not equal to 0. For our proof, we're going to use our theorem here that relates continuity to sequences, neighbors, and accumulation points. In particular, we're going to use sequences, so that is part B here. So let xn be a sequence of d converging to c. To show that f plus g is continuous, it suffices to show that the limit of f plus g of the sequence is equal to f plus g of c. We can take our limit of f plus g of our sequence xn, and we can split it up into the limit of f of the sequence plus g of the sequence. And this comes from our properties of limits of sequences. Continuing, we get limit of f of our sequence plus limit of g of our sequence. And then because f is continuous and g is continuous, where do we have that? Somewhere we talk about that. F and g are both continuous, then the limit here is f of c plus g of c, which is equal to f plus g of c. The proof for the product and quotient are similar. The only thing you need to watch out for is for the quotient, you need a sequence that does not equal 0 for all n. Next, we have a theorem that says the composition of two continuous functions is also continuous. So our details of this theorem, we have two functions, f and g, and f maps from d into a set that is into the real numbers, but in particular, a subset of the real numbers called e. And then g maps from e to r. We said that f is continuous, so it's continuous at point c, so it maps over here to f of c, and g is continuous at f of c, so it's continuous here and it maps. So we have our function composition g of f of c. And by our theorem, because f and g are continuous, we expect this g of f of c to also be continuous. And what we're going to use for this proof is this theorem here, the part that relates continuity to neighborhoods. So for every neighborhood v of f of c, so here we have our neighborhood v, which is around f of c, somewhere right here, and here's our f of c. So for every neighborhood here, there's going to be a neighborhood u of c. So that's down here. This is our neighborhood u of c, such that the image of f of u intersected with d is a subset of v. So in other words, we can find a neighborhood around c that when we map f of c, that image is totally contained in v. And that's what it means to be continuous. When we apply our theorem here with the neighborhoods, to our current theorem of our function composition, we're going to kind of work backwards. We're going to go from this resulting g of f of c to get back to this neighborhood here. And then our next step will be to go all the way back to d. But first we're going to start here. We have g of f of c, so our very ending neighborhood v. So I color-coded them in blue. So for every neighborhood of f of c, in this case this is a neighborhood of g of f of c, our function composition, there should be a neighborhood of c. So that's color-coded in green. This is our neighborhood of f of c that gets mapped to g of f of c, such that the image of this neighborhood intersected with d is a subset of v. So in other words, here we want the image of this neighborhood to be totally contained in this neighborhood w. So again, writing this in words, let w be a neighborhood of our function composition, g of f of c. That's this blue neighborhood. Since g is continuous, then we know that there exists a neighborhood v of f of c, that's in green, such that the image of v intersected with e is totally contained in w. So we know this is true because we're given that g is continuous. So far we've seen that we've used the fact that g is continuous to get this neighborhood, this green neighborhood, mapping completely into this blue neighborhood. And we know this is true, or we can find these neighborhoods, this green and blue neighborhood, because g is continuous. Now we need to go all the way back here to the start. So we're going to let our green neighborhood, again, this is f of c. There's a neighborhood of c, this yellow neighborhood, such that the image of this yellow neighborhood u with the intersected with the domain is a subset of the green neighborhood. And we know that this is true because f is continuous. So writing this down, since f is continuous at c, there's a neighborhood u of c, this yellow neighborhood, such that the image of u intersected with d is totally contained in v, this green neighborhood. And now what we have is that this yellow neighborhood u, if we plug it into g composed of f, that its mapping will totally be contained in the blue neighborhood w, which is exactly what we want to show if we want to show g of f of c is continuous at c. And I have to apologize because I'm so used to drawing things of sets and functions mapping in this kind of blob sort of way. Almost looks more like the neighborhoods are these two-dimensional things, as if you're in the complex plane or something, but you're not. You're in the real number line. So I did draw these out. So my sets are sets on the real number line. Here's my set D, E, and R, and then I have my neighborhood of C. C is in my set D, and my neighborhood of C is in yellow, and then I map this neighborhood from D to E, and I map the neighborhood of C to f of C, which is in green, and then I map to the real numbers with g of f of c, which gets mapped to this neighborhood in blue. I just wanted to make sure I did draw this at least once with these neighborhoods on the real number line instead of with this blob interpretation. For an example of our composition of continuous functions, we're going to let g of x equal to sine of x, h of x equal to 1 over x, and I of x is equal to x. So for all x not equal to 0, we have x, that's our function I, times sine of 1 over x is equal to I, our function I, times g of h of x. And I broke it down a little bit here, my g of h of x. So my h of x is 1 over x. So now I have g of 1 over x, which is equal to sine of 1 over x. So you can see how x sine of 1 over x is equal to I times g of h of x. Now if we assume sine of x is continuous, then x sine of x is continuous by our theorem here that the product of two continuous functions is continuous. And again, we're assuming x is not equal to 0. So it follows that x sine of 1 over x, again now we're introducing our function composition, But if 1 over x is continuous for x not equal to 0, then sine of 1 over x is also continuous for x not equal to 0. So x sine of 1 over x should also be continuous as long as x is not equal to 0. And we can define f of 0 equal to 0. Now we have a theorem about continuity and pre-image of open sets. So if we have a function f from D to R, it's continuous on D if and only if every open set G and R, for every open set G and R, there exists an open set H and R such that H intersect D is equal to the pre-image of G. So here we have a function that goes from D to R, and if we have an open set G and R, then there must exist an open set H and R such that H intersect D is the pre-image of G, the pre-image of F and G. And the corollary is if F goes from R to R is continuous if and only if the pre-image of G is open whenever G is open. And the example is to show you that when this doesn't happen, that the pre-image of an open set is not an open set. And of course, we can't do this with a continuous function, but we can show you how a discontinuous function might fail to have a pre-image of an open set be open. And for this example, we're going to consider f of x is equal to x if x is less than or equal to 2, so it's this line here, up to and including the point 2, and x is equal to 4 if x is greater than 2. So obviously you can see f is not continuous, and because it's not continuous, it can fail to have the pre-image of an open set be open. If it were continuous, then that would not happen. But it's discontinuous, so we're going to look at that. We're going to look at an open set G going from 1 to 3, not including the endpoints. And we're going to see that the pre-image of this set is not open. In particular, you can see the pre-image is going to be for 1 to 3 are the points, and here because this is open, so we don't include the 1, so the first part is open, but then over here it actually does include the point 2, so it's closed, it's half open, half closed. So here we have an example of a discontinuous function where we have an open set and its pre-image is not open. For a continuous function, you will never have this type of condition. And now we have talked about continuous functions. We've talked about how continuity relates to sequences, neighborhoods, and accumulation points. We've talked about discontinuous functions. We've talked about the sum, product, and quotient of continuous functions, as well as continuity of the composition of two continuous functions, and continuity and how it relates to the pre-image of open sets. As far as proving continuity, usually it's a little bit obvious if you want to use this composition of functions. The sum, product, and quotient of continuous functions allow you to break things down. But if you just generally want to prove continuity, you can do this by the definition of continuous functions. And in this theorem here, continuous, this one's a little bit hard because you have to show this, this x of n as any sequence. So this is kind of a difficult proof. The neighborhood one is an okay way to go. We saw an example of this. And this one here is also a very good way to go, to use this criteria. As far as this is concerned, I said this one's difficult because you have to show this is true for any sequence. But what you do get is the theorem for discontinuous conditions, which is that you have a sequence that converges to C, but the f of xn does not converge to C. So it's kind of like the opposite of this. So instead of using this to prove continuity, often you use the opposite, the negation, to prove you have something that's discontinuous. And here I have 3 problems for you to try. So you can pause the video, give them the try, and on the next slide I will have solutions for you. Here are the solutions. And that is it for this video. Thank you for watching.